Hey guys, in this video we're going to be looking at molecules, ions, and ionic compounds. So at the end of this, we want to be able to distinguish between a molecular and ionic substance in terms of their composition. We want to look at molecular and structural formulas. We want to summarize how elements gain or lose electrons to form ions, and then using our periodic table, determine what our common ions are, and then lastly, determine the empirical formulas of ionic compounds giving their component ion charges. So when we talk about an ionic compound, we're talking about a compound that's formed from ions. So ionic compounds are made up of ions, and they're held together by electrostatic forces. So our positive cation, negative anion are going to be attracted to each other, and this attraction that we see is a bond formed. So our ionic bond. So it's just those positive and negative charges together that form that ionic bond. Ionic compounds are made of metals plus nonmetals. Made of metals plus nonmetals. Okay. And they are not going to share electrons. Electrons are going to be transferred from one to the other. Specifically, electrons are being transferred from the metal to the nonmetal to form our ions. So electrons are transferred from the metal to the nonmetal. And this forms ions. And this is how we get our ionic compound. This is different from covalent compounds. In a covalent compound, electrons are shared. And those shared electrons are what make up the bond. Okay? We oftentimes call an ionic compound a salt. So we talked about in a previous video the idea that halogens are salt forming. So a salt is a substance formed by a neutralization reaction, and a lot of those halogens are formed or are part of neutralization reactions because they're in acids. So a salt is the product of an acid-base neutralization reaction. Okay. When we think about an ionic compound, it is going to be an extended structure. So it's going to be extended in all three dimensions. And we don't have discrete molecules like we have with covalent compounds. So that's why we give the empirical formula, because we have atoms beyond count in ionic compound. So we want to show the smallest whole number ratio of those atoms. Okay. So our properties of an ionic compound is they are going to be high melting, high boiling. They are going to be brittle and hard. They are going to, for the most part, be soluble in water. and they're going to be insulating as a solid, though they're going to be conductive in a liquid. So conductive if dissolved. And we'll talk about why in a further lecture. Okay, so let's look at our cations, our positively charged ions, and our anions are negatively charged ion. So any ionic compound is going to be formed of cations and anions. So those together, and they'll be added in such a way that we have a neutral species. Cations and anions can be formed with just about any charge, as long as it's a whole charge. So integer values, generally they're going to be between 1 and 3, either positive or negative, although you will see some different types. So a cation will be formed when a metal loses an electron. And it could lose an electron or electrons. Okay? And it's always going to be the metal. The nonmetal is not going to lose electrons. Nonmetals do not become cations. The anion is formed when a nonmetal gains an electron or electrons. And the charge is going to be equal to whatever, the magnitude of the charge is going to be equal to however many electrons it gains or loses. Okay, now as a note, you never form an ion through the gain or loss of a proton. Remember, if we lose or gain a proton, we do not form an ion, we form a new element, which only occurs during nuclear reactions. So these are not going to occur during chemical reactions, which is kind of what's going on when we're gaining and losing electrons. Okay, so let's look at how they are formed. When we have a metal and a nonmetal in contact with each other, an electron can be transferred from that metal to that nonmetal. Okay, and when we have that occur, the overall charge of the compound is going to be neutral, or 0. So we're going to do this again in such a way that at the end, our compound itself will be neutral. If it's not neutral, it will not be considered a compound. An example of this is if we have sodium. Sodium has 1 electron, and chlorine has 7 available bonding electrons. And again, this is something we'll talk about a little bit more, but that sodium will give up that electron to the chlorine and will form a sodium plus and a chlorine minus. And this is our ionic compound. Okay. So we have what's called simple ions, and these are going to be ions that we can determine just by looking at our periodic table. So these are going to be our main group right here. So if we are in group 1, we're going to form +1 ions. Group 2, plus 2, and then group 13 is going to be plus 3. In our group 14, no ions generally, although some of our larger atoms will form plus 2, plus 4 ions. But those are not our common simple ions. And then group 15 is going to be minus 3. Group 16, minus 2. Group 17, minus 1. And then our group 18 again, no ions. Our transition metals, our non-group, are going to have a variety of charges, but there are a few that will always form the same charges, and that's these three right here. So zinc will always form a plus 2 ion in compounds. Cadmium, same thing, always form plus 2 ion in compounds. And silver will always form plus 1 ions in compounds. So these you should be aware of when you're looking at your periodic table. You should be able to find your plus 1, plus 2, plus 3, minus 2, minus 1, and then you should commit these three to memory as well. The most common charges are going to be between positive 1 and positive 3, or negative 1 and negative 3, but you will see a variety of different charges when you look at your transition metals or your lanthanides and actinides. So this is just another periodic table that just shows the main group ions that you should know and be able to come up with every time. The next thing we're going to talk about is polyatomic ions, which are the same as molecular ions. We call these molecular ions. And we call these molecular ions because they are atoms that are covalently bonded. And they're almost always just nonmetals, although there are the occasional metal in there. Okay. And our polyatomics are going to act as a single unit. So it is very unlikely that we're going to break them down. So don't break them down. Unless during a chemical reaction they are actually broken down, but that rarely ever occurs. Okay. They are different from a compound because they have an overall charge. Okay. And the charge itself belongs to the entire unit. Okay. Now this is a very large chart. There'll be a chart on D2L as well with all of your polyatomics, and you need to memorize these. These should be part of your memory by the end of this class. Now, it's kind of hard to memorize all those, so to kind of help you a little bit, I've added in this chart so you can see some common polyatomics, and hopefully it'll help you to memorize their charges and such. For instance, here is chromate and permanganate. They are both 2 minus, and they both have 4 oxygens. Then we go over here. Borate, carbonate, and nitrate goes 3, 2, 1. We also have phosphate, sulfate, 3, 2. Then these other ones are a little less important. So if they're not on the chart, they're not ones you need to memorize, but they are, as you can see here, going from 3 to 2 in all of these cases. And with our manganate and bromate, they both have -1 with the 3. Same with the iodate. Okay. There are some additional things we can do to memorize the other ones because these are just one example of the charges. And again, hopefully you can see from here, there are some examples where we have different numbers of oxygens. They're always going to have the same charge, but they might have different amounts of oxygens. And there'll be other strategies to memorize those, which I'll talk about in a little bit. Okay, so let's look at our strategies for forming ionic compounds and balancing charges. When we talk about a chemical compound, unless we're talking about a polyatomic, it's going to be neutral. So compounds are neutral. So when we're forming an ionic compound, the overall charge has to be neutral, so we need to make sure that the anion-cation ratio are such that when at the end, our charge is neutral. So not all ionic compounds will have a 1-to-1 ratio of cation to anion. It depends on the charge. Okay. So, for instance, if we take Na plus and Cl minus, they have equal and opposite charges, so they will be 1-to-1 in NaCl. If we take Mg2 plus and 3 minus, this becomes more difficult. By the way, you should be able to use the periodic table to come up with these numbers. Here, what you're going to do is you're going to take the magnitude of the charge, and it's going to become the number of the other ion. So this becomes Mg3 and 2. If you come up with something that is not the empirical formula, so it's not the smallest whole number ratio, make sure to divide. For instance, if you had something like something like this would give you Al3 and 3, then you divide by 3 to give you Aln. Sometimes you're given a chemical formula and you need to determine the charges of the ions themselves. So we're going to go from chemical formula to ion charge. Okay, and we do this by thinking about our known ion charge. There's always going to be at least one of them that we know the ion charge for, and use that to solve for an unknown ion's charge. And we may know both ions' charges if they're both main group elements, but if they're not main group elements, we might have to determine the charge. So if we take AX, BY, we know that the overall charge has to equal 0. So that will be equal to X times by charge on A plus Y times by charge on B. Keeping in mind this should be negative, this should be positive, as we always write our cation first, our anion next. We could take something like this and determine the charges. Oxygen is a main group element, so we already know its charge. It should be -2. So we're going to say 0 is equal to 2, our X, times by whatever our charge on iron is, plus 3 times by our charge on oxygen, -2. And solving for this, we get an iron charge equal to +3. Okay, let's look at our covalent compounds. Covalent compounds, in contrast to our ionic compounds, are composed of nonmetals and have bonds that are not ionic in nature. So we're going to have no ions here. Here we're going to have elements. So keep in mind there are no ions within covalent compounds. And we're going to look at two types of covalent compounds: organic and inorganic. Organic, these are going to be carbon containing. And then our inorganic are non-carbon containing. Okay. And as a note, inorganic compounds can be ionic or covalent. Okay. Here are a couple ways that we can picture our covalent compounds. So we have first a structural formula. That's this one right here. And this is where we have atoms attached, and we show the attachment through lines, and these are going to represent bonds. So it shows which atoms are attached to which. And lines equal covalent bonds. Okay. And then, of course, the element symbols represent the atoms. Okay. This is nice to know what type of substance we have, and it can help us differentiate between different compounds more than just looking at our chemical formula. Our chemical formula just tells us types of atoms and how many of each. It does not tell us how the atoms are bonded to each other. But these covalent compound pictures that we're showing today actually show that bonding. Our next is our perspective drawing. And it shows a 3D shape with bond angles. So it's structural plus 3D with bond angles. So it attempts to show what's actually going on in space within the molecule. Next is our ball and stick. And here we get rid of those element symbols, and we instead have our balls being representative of what atom. So we have no more element symbols. Instead, atoms are drawn as colored balls. Okay, so generally, hydrogen is white, carbon is black, oxygen is red, and nitrogen is blue. Okay, and it's also a 3D shape with bond angles. And then our last one is a space filling model. So it's just like our ball and stick, but now we're taking the atoms and trying to show theoretically what size they are, so relative sizes. So it's just like the ball and stick, but attempts to show relative sizes. So let's look a little bit at organic chemistry. Organic chemistry is the study of carbon-containing compounds. So these are going to be what we call hydrocarbons because they also have hydrogen. So it's going to be a hydrocarbon and hydrocarbon derivatives. So a hydrocarbon with one of these other elements we see on this periodic table to the left. So both of these are considered classes of organic compounds. So we call them organic molecules. And there's a whole branch of chemistry there's a whole branch of chemistry devoted to the study of these hydrocarbons. So this is the hydrocarbon CH4. It is probably the simplest of all of the hydrocarbons. And we call anything that has just carbons and hydrogens and only single bonds, so bonds that only have one line, we call these alkanes. We can have other elements in here, other atoms in here, like oxygen, hydrogen, but the alkanes means that we have a hydrocarbon with single bonds specifically. So that means each carbon in this structure has 4 bonds. So it's going to be attached to 4 atoms. So if you look at a hydrocarbon and you don't see each carbon attached to 4 different atoms, it is not an alkane. It is one of the other types of organic compounds, and there are many. We're not going to go very far into this. So here are some of our alkane derivatives. So adding in that heteroatom. And a heteroatom is any atom besides hydrogen and carbon. So oxygen, bromine, nitrogen, those type of things. So most common heteroatoms are oxygen, that's probably the most common, nitrogen next, and halogens. So there are many halogens within organic compounds. Okay, and generally when we take a single hydrogen and replace it with a heteroatom or a group of atoms, we call that a functional group. So, or group of atoms with a heteroatom. This is called a functional group. Okay. And the last thing I want to talk about is the idea of an isomer. So similar kind of concept to an isotope, right? So similar things, just slightly different. With an isomer, we have the same molecular formula, so the actual chemical formula will be the same, but we have a different arrangement of atoms, which is why it's really nice to show these atoms with the bonding. So isomers are compounds with the same molecular formula, but different arrangements of atoms. And they are going to have significantly different chemical properties. They might have different densities, definitely going to have different boiling points and melting points and different reactivities. Here is an example of three isomers of C3H8O. So by just writing the chemical formula C3H8O, we don't actually know what the look of these compounds are until we draw them out. So this is 1-propanol, 2-propanol, and methoxyethane. So three different ways of drawing these structures that have very, very different chemical properties. Okay, that's it for our compounds and molecules for ionic and ionic and covalent substances. I will see you guys later. Bye. And that's it for ionic and covalent compounds and molecules. I'll talk to you guys later.